If you work in the world of optics, there's a good chance you may know a thing or two about aspheric geometries, but there's also a good chance you may not know just how quickly and easily you can analyze the measured data for these geometries using OmniSurf3D. So to demonstrate this, I purchased a simple aspheric lens from our friends at Edmund. It's a plastic molded lens and measured it here on the Z gauge. We're going to use this to demonstrate just how fast we can pull off an analysis and how visual and intuitive it is along the way. So for no cheating, I'm going to close this window, I'm going to close this, and I'm going to clear out all the settings and data from OmniSurf3D so we can start from scratch. So I have a simple measured data file, and I have OmniSurf3D, and I have a drawing for the surface that we measured. So let's drag in that measured data file first just to see what it looks like. Now OmniSurf3D gives us a chance to see the raw data and all the steps along the way of our analysis. But for right now, let's look at the raw data, and we might see a few missing pixels. In fact, we can right-click and look at properties and see that there were 4 missing pixels out of the 1.5 million that were measured. So our next task is to set things up for this analysis. For pre-processing, let's use bicubic filling of that those missing pixels. And now for our geometry, we're going to set up an asphere. OmniSurf3D uses the standard asphere equation. So let's grab this drawing that came with this particular lens, and we see that the equation is of the same format, so our coefficients should drop in easily. Let's grab the coefficients from the drawing. I'm going to copy those to the clipboard, and I'm going to use Notepad++. You can use any plain text editor to do this step, but I'd like to paste them into this plain text editor so I don't get any formatting when I copy these coefficients into OmniSurf3D. So we'll grab the curvature, let's grab the conic, and paste these in. Now in an editor like Notepad++, I can hold down the alternate key and grab the polynomial coefficients all in one block and paste those in. Now we can verify that the 14th order is -9.5 10 to the minus 16. We can go to the drawing, and that's the L term, and we can see the L term is indeed at the 14th order here. So those look right, but we also have the ability to plot the current asphere so we can see if things are looking right based on our coefficients, or we can do a sag test at a given point. For example, let's look at x equals 4 millimeters, and we can see the sag at that point and compare that to your model. So there's a way to validate that we've done things correctly at this point. So we've configured our asphere. Another part of our geometry configuration, though, is how are we going to look at the errors relative to this nominal asphere? We can look at the errors perpendicular to the surface, so each data point is mapped onto the surface, and then that is all unrolled to a new error surface that's actually bigger, perhaps, than the surface we measured. Well, bigger, yes, but maybe not visually bigger, because sometimes we're dealing with very flat surfaces, but in other cases we'll notice that using perpendicular residuals, the unrolled surface gets much larger. The other option, though, is we can look at vertical residuals, look at the errors along the optical axis, and in this case, our error surface will be the same width as the measured surface. For fun, let's look at perpendicular. Now we'll skip filtering for now. Let's look at the raw leveled data and calculate some parameters on it. Let's look at the total peak to valley, or many people are now using the term SZ instead of ST. Z is the total height, T is also the total height, so these will be the same. And let's look at RMS, SQ, and go ahead and OK this analysis. With those configuration steps, we've now analyzed this surface. We've taken the raw data and pre-processed it, so we filled in the holes. We've put a geometry through that. Our asphere now is showing the nominal asphere as a blue transparent surface, and then we can look at the form removed surface and see that we've flattened out the asphere, and we're now looking at the errors relative to that model. We see the errors are actually concave with some spikes all over them. Now, since we've not applied any filtering, our primary surface is the same as form removed, and our filtered surface is the same as form removed. Now we can make some improvements here. What we can see is this surface with this concave residual, its radius of our measured surface doesn't match the radius of the model on the drawing. So let's fix this. Let's go to settings and go back to geometry, go back to our asphere configuration, and this time let's tell it to optimize the radius. We're going to start with this radius, but let OmniSurf3D optimize it from there. So let's OK this and see what happens. When we do this, our filtered surface now is much flatter, and we can start to see the spikes and the noise, kind of the salt and pepper noise along the way. Now, many times people will use a median filter to go after this, a 3x3 or a 5x5, but I've liked the use of a robust short filter for this. So using our short filter, our filter that kind of denoises the surface, a robust filter of maybe 8 microns, does a nice job with removing these kinds of spike noise features. And sure enough, that is the case with this particular surface. So now we can see the machining marks within the mold that made this molded optic. Pretty interesting. Our ST or our SZ value has gone down considerably from the 6 or so microns we had before to less than a micron now, but we see most of that is due to the corners of this particular measurement. Let's use the data cropping tool, and now let's select a circular region instead of a square region. Holding down the control key forces us to be square as opposed to just grabbing a corner. We can make ellipses and weird shapes. So let's hold down control and make a circular region somewhere in the middle here, and we'll OK that, and our analysis now removes the corners and looks at only the middle, and we see the surface is becoming very, very good in terms of form error. Another thing we might want to do, though, is remove these tool marks. We can see the machining marks from the mold that were transferred onto the lens. Let's filter a little bit harder. Instead of 8 microns, let's maybe use 80 microns. And now we'll see just kind of the mid-spatial wavelengths on the surface, not those marks from the actual machining. Another thing we could do in cases of machined surfaces like this is actually remove the center and perhaps remove some of the errors that may not be influencing us optically, kind of looking at a clear aperture kind of situation. So we do that, and we can now get rid of some of these errors in the middle and see our form error go down even smaller as we look at perhaps the effective area of the surface. So nonetheless, we've looked at configuring an optical component in OmniSurf3D's asphere settings. In these settings, we can choose perpendicular or vertical residuals and configure the asphere accordingly. But what do we do with this shape now that we have it? We can do some other modeling. For example, we can take this shape back into your optical modeling software and see how it actually affects your design. So we can do a couple of things in this regard. We could look at Zernike's of the residuals. So here are our Zernike coefficients. Those can be saved out to a table or simply copied to the clipboard for pasting. Or we can actually export this filtered surface, and we can export it out as XYZ, for example, if your modeling software takes that shape, or even a Code 5 INT file to drop straight into that software. So there are lots of options for exploring your aspheric data and even exporting it back out into a world where you can see the influences of it or even do machine corrections with it. OmniSurf3D is incredibly powerful, incredibly easy to use, and super fast. So let's see just how fast things are. I'm going to set my cropping back to all data since my measurements are of different areas. And let's drag in some other measurements. I have a batch of measurements, and let's just simply drag and drop into this new configuration and see what these lenses look like. So these particular geometries are different measurements on this surface, and with a simple drag and drop, all of the settings that we've set up are now being applied to these data files as we go. We can even do this in an automatic way where we can batch process several surfaces from a given folder into one particular results file. So OmniSurf3D truly makes aspheric analysis simple, graphical, visual, and even more important, very, very fast so you can get on with your job. If you have any questions or would like to explore your data further using OmniSurf3D, please check out the 10-day trial at digitalmetrology.com or reach out to us there. We'll be happy to help.